Hey guys, welcome to a continuation of question 3 for the 2019 Level 2 Electricity and Magnetism paper. So question 3, magnetic fields. The magnetic North Pole, also known as the North Dipole, is a point on Ellesmere Island in the northern Canada. Here, the Earth's magnetic field lines enter the ground vertically. The strength of the magnetic field there was measured at 47.3 times 10 to the power of negative 6 Tesla. A bicycle has metal handlebars that are 42 centimeters wide. A student riding the bicycle on the island rides on a flat ground at 13.5 meters per second. Alright, question 1. Show that the voltage induced across the handlebars is 2.68 times 10 to the power of negative 4 volts. So we know that the voltage is described with the relationship of V equals to BVL, where B is our magnetic field strength, V is the velocity, and L is the length of the conductor. So 0.42, remember, 42 centimeters is equal to 0.42 meters. Very important to convert it to meters to get an accurate answer. So 0.42 times of the magnetic field strength, which is 47.3 times 10 to the power of negative 6. So times 47.3 times 10 to the power of negative 6. Multiplied by our length of the conductor. Oh, sorry, we already did that. So multiplied by the speed, which is 13.5. And that does indeed give you 2.68 times 10 to the power of negative 4 volts. And that would be 3 significant figures. And in terms of grades, that's just an achieved. Give an in-depth explanation on how a voltage is induced across the ends of the handlebars. Alright, so this is a pretty standard question that appears in many of the past year papers. So an in-depth of how the voltage is induced. So basically, when the conductor moves across the magnetic field, there is a magnetic force that is experienced by that conductor. Because there are many electrons inside this, let's just say this object is neutral. However, it does have both protons and electrons. When the conductor moves through the magnetic field, there is a magnetic force that is experienced by those electrons in the conductor. So they will begin to move towards the direction of where the force is felt by the so they will move in the direction of the force. And the protons won't move, and therefore one end will become positively charged and one end will become negatively charged, and this creates potential difference as well as charge separation. So therefore the conductor will begin to act like a battery. So basically you can link this back to the static electricity where the electric field is generated. Hence a voltage will be induced. So in this case, we can actually find out the directions that the electrons will be moving in. So in this case, we'll be using our right hand step rule. So we have our magnetic field lines going into the page. We have our movement of the conductor is in the right direction. So remember, your fingers are pointing into the page, and we're going to use our backhand step rule. So we're going to use our backhand is pointing in the direction of the motion. So basically, your palm will be pointing left, and your back of your palm will be pointing right, because that's the direction of the movement. Alright, so in this case, we have our conventional current going upwards. Sorry, so it's upwards. Okay, so in this case, we have our positive here and our negative here. That's because our positive is going upwards across to our negative. So if I put this in a loop, then it should look something like this. So using our conventional current rules. So therefore, by using our right hand step rule, we can see that technically it's the right hand back step rule. So by using this rule, we can see that the force experienced by the electron is actually downwards. So give an in-depth explanation. So basically we can say, when the conductor moves through the magnetic field, there is So basically, when the conductor moves through the magnetic field, there's a magnetic force experienced by the electrons inside the conductor. By using right-hand side rule, this force is downwards. Hence, okay, so this causes charge separation. Charge separation and potential difference. And an electric field is generated. Hence voltage induced. Alright, so basically when the conductor moves through the magnetic field, there is a magnetic force experienced by the electrons inside the conductor. By using the right-hand step rule, this force is downwards, hence the electrons will move downwards, leaving the top positively charged and the bottom negatively charged. This is caused by charge separation and potential difference, and an electric field is generated, hence voltage induced. And if you describe up to here, you should get a merit grade. In terms of getting an achieved grade, if you can describe that the electrons have been moving down using the right-hand step rule, so up to here, maybe that should get you an achieved. Alright. The student then rides up a steep hill at 13.5 meters per second. What is the effect of riding up this hill on the value of the induced current? Alright, so many people said this was a challenging question. However, you can remember that the maximum voltage can only be induced when a conductor is cutting the magnetic field lines. So as you can see here, the magnetic field lines are vertically downwards. However, originally the bike was traveling here. Sorry, that's terrible drawing. Originally the bike was here, and it was traveling perpendicular to the magnetic field lines. So basically, in other words, it was cutting the magnetic field lines. When this happens, this is the case when the maximum voltage can be generated. However, when it goes up the steep hill, it no longer cuts the magnetic field lines. So it's no longer cutting the magnetic field lines. It's now, when the lines are here, there's now an angle it's not 90 degrees. It's let's just say it's angle theta now. And this means that the maximum voltage will no longer be generated. So in fact, the voltage generated will actually be less in this case. So in terms of explaining it, we can just say that maximum voltage is induced when the conductor is cutting the magnetic field lines, and minimum voltage is induced when the conductor is parallel to the magnetic field lines. So when the conductor is parallel to the magnetic field line, then there's no voltage generated. However, when it's perpendicular, there's maximum voltage generated. Alright, so in this case, you can start off our answer by saying, maximum voltage is only when the conductor is cutting it only happens when it's cutting the magnetic field lines. Alright, so basically maximum voltage is induced only when the conductor is cutting the magnetic field lines. However, when the bike rides up the hill, it is no longer cutting the magnetic field. Hence, the maximum voltage is no longer induced, hence a decrease. So this should be a merit level question. And to get an achieved, for an achieved, basically saying maximum voltage is for an achieved, actually, if you just circle this correctly, this might just be an achieved by itself. I'm not sure. This potentially could be an achieved by itself, but perhaps to be safe, maybe to get an achieved, you can write maximum voltage is induced when the conductor is cutting the magnetic field. So maybe up to here should be good enough for an achieved. The student has an after-school job at a junkyard. While they move at a while they're there, they move a 1.5 meter steel pipe through a 0.8 Tesla magnetic field of width 1.2 meters at right angles to the field. The end of the pipe, actually, that's not even right. What am I doing? Hold up. Sorry guys, I'm just being stupid now. Alright, the student has an after-school job at the junkyard. While they are there, they move a 1.5 meter steel pipe through a 0.8 Tesla magnetic field of width 1.2 meters at right angles to the field. The ends of the pipe are connected to a circuit that is outside the magnetic field. The circuit has a resistance of 5 ohms. Calculate the force that the student needs to exert in order to keep the pipe moving at 3.1 meters per second at right angles to the field. Alright, so for this question, we want to find out the force needed. And we have our velocity equals to 3.1 meters per second. We have our length of the conductor. Remember, it's length of the conductor inside the magnetic field. Even though this length is 1.5 meters, this end here and this end here are not inside the magnetic field lines. So hence, there's no effect. So therefore, our length is actually only 1.2 meters. We also have our resistance is equal to 5 ohms. And that's all the information I have, I believe. Yes. Oh no, we also have that the B equals to 1.8 Teslas. Alright, so we know that F equals to BIL. However, we don't have current. We have the magnetic field strength, and we also have the length. However, we don't have the current. However, we know that current can be figured out using the I equals to V over R. However, we don't have voltage. So right now we're trying to work out our voltage by using the formula V equals to our BVL. So V equals to our velocity, so 3.1, times of our magnetic field strength, which is 0.8, times by our length, which is 1.2. And 3.1 times 0.8 times 1.2. And that should give us the voltage as 2.976 volts. So now we can substitute this 2.976 volts into the current. So to find our current, so 2.976 over 5. And that should give us our current should equal to 0.5952 amps. And now we can finally use our final step to find the force. So F equals to 0.8, which is our magnetic field strength, times by our current, which is 0.5952, and times by our length, which is 1.2. So 0.8 times 0.5952 times 1.2. And you should get that the force should be equal to force should be equal to 0.57 newtons. And this should be an excellent level question. In terms of getting an achieved mark, I think that's finding the voltage is enough to get you an achieved, and finding the current as a result should get you a merit. So achieved for the voltage, merit for the current, and excellence for the force. Alright, thank you for watching this video on the question 3 for 2019 level 2 electricity paper. I hope you enjoyed, and I hope to see you all in the next one. Thank you. Bye.